Hello and welcome. Today I'm going to talk about applications of GNSS or Global Navigation Satellite Systems in geodynamics. I write these applications in four categories: tectonic and seismic monitoring, environmental monitoring, natural hazard warning system, and geophysical insights. Tectonic and seismic monitoring. We know that the Earth's crust is divided into different tectonic plates, and this plate moves all the time due to mantle convection. And one way to measure these movements, or the plate tectonics movement, is to have GNSS receivers and monitor the changes in the coordinates that which are determined by the GNSS system. For example, as you see here, we observe that this plate is moving towards east, and also we see that the African plate is moving toward the Eurasian plate. And all these things are measured by the GNSS. Of course, there are mathematical models explaining this type of movements, but the best way to monitor the movements of tectonic plates is to use space geodetic techniques, and one of them is GNSS. And using GNSS, we can measure the coordinate changes. And from the coordinate changes, we can conclude that to which direction each plate is moving, or even if they rotate. As I explained, the tectonic plates are moving all the time or continuously. Any movement at the surface of the sphere or at the Earth can be considered as a rotation because the Earth is rotational. This rotation, as you see here, can be rotation of a plate around the rotation axis, or it can be a movement from one point to another. For example, this first plate from here moves to this position, and this movement is like a circle or like a rotation at the surface of the plate. This rotation axis intersect the Earth at a point which is called Eulerian pole or Euler pole. It means the rotation axis. You can compute this rotation axis using this formula. Simply here, it is that you have to do it by these two squares. You have the velocity, northward velocity, eastward velocity here, the rotation rate, and lambda and phi are the coordinates of the point at the plate, and lambda EP and phi EP are the coordinates of the Eulerian. Here I can show you an example. This was done by one of my friends. And we together, we did it for Iran. And you see these movements of the plates of Iran or Eurasian plate pushes the Arabian plate, pushes the Eurasian plate in that direction. And you can very well see a rotation type here and rotation type for here. And we have estimated the rotation rate and also the Eulerian pole and published this in this article. GNSS and volcano deformation. Consider that we have magma inside the Earth, and some movements from magma causes that the mountains expand, and after the extraction of magma, they contract again. This extension and contractions can be very well measured by GNSS receivers which are mounted at the surface of the volcano. At the left-hand side, you see the MOGIS model. MOGIS model gives you the change in the height and the radial direction. What is the radial direction? For if this is the source or the chamber of the magma here, the horizontal distance from the magma chamber is called R, or radial distance. So there are two types of movements at the surface of the volcano. This is vertical, which can be connected by or computed by this, and or horizontal, which can be computed by this formula. And here delta P is the pressure change inside the chamber, D is the depth, and A is this radius. If we consider that this is a sphere, or chamber is sphere, A is the radius of that sphere. So in practice, if we have these parameters and we have the pressure change, we can see how much delta H and delta R can measure or determine or compute it. However, we can do it in the inverse way. If we have changes at the surface of the volcano, delta H, and the radial displacement, we can go and determine these changes in pressure, depth, and the rate, and also the size of the chamber. This is an inverse problem. And post-seismic activities. Consider that when earthquake happens at this point here, what will happen? The earthquake will propagate through the crust, and we will observe some deformation or changes in the coordinates of GNSS receivers. Therefore, it can be seen that, for example, if we have some changes, let's say the coordinate changes in the Z direction, or vertical changes, or horizontal changes. As you see, point A is close to the earthquake center, and this point senses more variations in the coordinate than the points which are far from that. For example, point E is far from the earthquake focal epicenter or focal point. So in this way, somehow we observe some phase difference between when the earthquake happens and when its waves comes to the other points. In that way, somehow we can have some early warning system, so that if we receive this quake wave received to this point, we have enough time to warn the other places here that the wave is on the way towards them. Information monitoring of a network of Skåne area. Here is just an example in Scandinavia. In Sweden, here we have some tectonic movement observed in the southern part of Sweden. And this is a sensitive area, and these are the GNSS stations for monitoring the changes here. And you see the network of the GNSS station for monitoring such deformation here. Natural hazard warning systems. So what this with is an example. In a place which is called Lilla Edet, it's a small city in the western part of Sweden. You see the river, there is a river here. And this area is always in risk of landslide because it's so humid and it's close to water. And here you observe a GNSS network for monitoring the deformations due to a landslide. And we have had a project working on optimizing this network with my former student here. This is a tsunami. When an earthquake happens inside the ocean, it creates strong waves, and these waves move toward coast. In the case that we have a GPS or GNSS tsunami meter close to the risky area, when an earthquake happens, this sensor can sense the changes faster than the sensors that we have here. In that case, we have time. We can measure how long after this wave comes to the coastal area. Here you see a study which is done for a tsunami in September 2004. And here you see the tide gauge at the port close to the coast. And here is the tsunami meter with the GPS. And you observe that when the tsunami happens, slightly after it will be sensed at the coastal area. So we have a little bit time to warn people around that to leave the area. This is somehow it can be an early warning system. Environmental monitoring. GNSS and surface loading. We have lithosphere at the surface of the viscous mantle. We have GNSS receiver at the surface of this lithosphere. If I put a load on the surface of this lithosphere, this load pushes down the lithosphere into mantle. And this causes that mantle moves away from the load and cause some deformations. As you observe, the GNSS receivers are moving towards the load. So by changing the coordinates of the receivers, we can see how much the lithosphere has been deformed under this load. The mathematical model of this load is here. If you have the deformation here, or in geophysics we can say flexure, flexure, it has this mathematical formula with the load. Here we have spherical harmonics at the coordinates latitude theta and lambda as longitude. And here is the density of the load, and this is the height of the load in the spherical harmonic coefficients. There are other methods for explaining this relation, but here I am more confident. It's more convenient for me to work with spherical harmonic. And here you see a CN, which is called compensation degree, which involves mechanical properties of the lithosphere. For example, the thickness of lithosphere or elastic thickness of the lithosphere is one of the parameters for that. Young's modulus and also Poisson ratio are the other parameters of the lithosphere. So, for example, I use this mathematical formula for determining the elastic thickness of the lithosphere based on the gravity data. GNSS and terrestrial water storage monitoring and atmospheric loading. As I explained, any load at the surface of the lithosphere causes deformation. Here consider the GNSS receiver, and we have a load here, and when the amount of the water or volume of water or atmospheric load increases, this causes that the land deforms. And again, the GNSS receivers shows coordinates that are getting closer to the load. Here's another example, which is done by Heki and Jean. And as you see in the Amazon area, when we have the load, and that you see that these arrows are showing the direction towards the load, and when the water is gone, they move away from the. It's for the horizontal deformation and for vertical deformation the same. When the load is coming and the water coming and they push the lithosphere downward, and when the load is gone, they show movement upward. This is in glaciology. For example, over areas like Greenland and Antarctica, we have GNSS receivers monitoring the changes of the ice by changing the coordinates of the receiver, which are measured by GNSS. Any type of deformations that happens there can be monitored by these GNSS receivers, even ice deformation or icequakes. The principle is very similar. Sea level change. Consider that we have a GNSS receiver on a boat or vessel. If we have anchored this vessel so that we do not let it go too far from the point, with the GNSS receivers that we have in the coastal area, the GNSS receiver that we have over to the boat, we can measure how much the boat goes up and down. And with that, we can measure the sea level changes. Of course, we can measure the tide, but tide is rather known for us. We can remove the tide effect and look at the other causes for sea level changes. Also, as you see here, the satellite signals can come to the water and reflect it back to this reverse antenna. In that case, by comparing the signal coming directly from the satellite to the upper antenna and the one which are reflected back from the water to the inverse or reverse antenna or lower antenna, we can determine how much the sea surface went down, how much sea level has gone up and down. It somehow is called GNSS tide gauge. For example, at Onsala Space Observatory, we have this system, and we have also a normal tide gauge there for measuring the sea level changes by GNSS. This principle is called also GNSS-R, which is GNSS reflectometry. Geophysical insights. Static adjustment. Consider that there is a load at the surface of the lithosphere and pushes down the lithosphere into the mantle. And we have GNSS receiver at the lithosphere. Now, after a while, when the load is gone, the mantle pushes back toward the north and causes some deformations to the surface of the lithosphere. As you see, in that case, the GNSS receivers go away from the load place. For example, in Scandinavia, we have land uplift model. 20,000 years ago, there was a big ice cap here. The center or highest point was here, close to that place, which is around the city Umeå. And now this ice is gone, and the land is trying to go back to this equilibrium or to the balance again. And this is what we have observed with GNSS receivers here, as you observe it. And as I explained, all this GNSS receiver shows movement away from the load. One of the simplest methods for determining upper mantle viscosity is to use this formula. This formula actually is an approximation, but it's rather good. If we have the geoid height from, for example, from satellite gravimetry, and the height, GNSS height rate of change, or lambda uplift rate, G is constant, gravitational constant, and gamma is the normal gravity, and you can determine the viscosity. You can have a look to the link here, so I cannot open it. And here you will see a map of viscosity determined over Fennoscandia. You will observe that the places that which has low viscosity, it means that they are the places that the mountains could penetrate more into the mantle. So in that way, somehow it tries to connect the viscosity to the isostatic principle. So the places that the mountains can penetrate more inside the mantle has lower viscosity than the places that they are flat. GNSS and mantle convection. We know that due to the heat inside the core, there are convecting flows inside the mantle. And flows are in two ways. They are moving like that, which are called toroidal, or they are like that. These are called poloidal. And for determining the mantle flow, we need the velocity of the points at the mantle, which we normally use GNSS for measuring them, gravitational potential of the Earth, and its radial derivative, which is gravity. We can, for example, use satellite gravimetry for obtaining them. And also we need the density contrast and viscosity, which we use geophysical models. Here you see the map of the stresses that I have computed. As you see, observe here, there are places that they are close to boundaries. This tectonic going to have high stress here. You observe these stresses here. What I'm going to say is that the velocities actually of the mantle, upper part of the mantle, actually the same with the velocities that we measure by GNSS and tectonic plates. For tectonic plates, the gravity is simple. We can determine the global gravity using satellite gravimetry, and we already have some information, the density and viscosity. Estimation of wall and length of day. We know that there are three types of movement in the Earth's rotation axis: precession due to the sun, nutation due to the moon, and polar wobble due to the homogeneity of the masses of the Earth. Some places of the Earth are heavier than the others. This causes extra movements in the Earth's rotation axis, which is called polar wobble or polar motion. So here in this study, as you see, I have referred to here, they try to write a mathematical model for the phase differences so that the satellite coordinate, receiver coordinate, perturbations to the satellite receiver clock errors, ambiguity, and also Earth's rotation parameters and atmosphere are all involved in one equation. And by this equation, they try to regenerate the phase differences. And based on that, this observation equation solved for these unknown parameters of the. It's a joint adjustment for that. Or the other studies say that, okay, they have the coordinates, the inertial system and coordinate of the earth-fixed system. We have these transformations, and based on these coordinates and these coordinates here, both sides we have, we can determine the coordinates of the pole, which are here, by solving this transformation or inverse solution to the transformation parameters. And also, the length of day can be determined based on this formula that is. And the longitude that we measure by GNSS has a direct connection to UT1. So we can determine the length of day as well using GNSS. We know that these days GNSS receivers are mounted to all satellite gravity missions or satellite gravimetry missions for their orbit determination. The orbit determination, GNSS is used. And all the perturbations of the satellite are measured precisely using these GNSS systems, as well as some other extra observing system. For example, in gray sky, we measure the distance between the satellites as well, or in both we had gradiometer. But in all of them, we need the position of the satellites. And the best technique for measuring or determining the position of the satellite is GNSS. And I can say that indirectly, we use GNSS satellite for measuring the gravity field of the Earth. And nowadays, by analyzing or orbital analyzing of satellites, we can determine gravity model for any type of satellite mission, but based on the orbit only for low degree harmonics or low frequency component of the gravity. And these are the references that you can have a look, and some other references that I have used so far. Thanks for your attention.